Hi guys, it's Steven here with part 2 of the tutorial. We're going to go over chapter 10 solutions. Before I get into the solutions, feel free to skip to the questions that you want to look at first, but I highly recommend looking at all of the questions that I go through, or sticking around for all of the questions or all the entirety of the video, because I'll be giving like my thought process and tips that I use when I'm solving these kinds of questions. All right, so the questions I'm going to cover are questions 1 or 10.1, 10.2, 10.3, 10.5 to 10.10, 10.14, 10.16a, 19, and 20. A lot of these questions involve, before I get into it, a lot of these questions involve a lot of calculator or a lot of calculations that you need to enter into your calculator. I know it's a lot, but it's good practice, and I think that it's good to carry out the computations instead of just leaving them in a bunch of terms. Excuse me. All right, so question 1. Consider the joint probability distribution of x and y from exercise 9.7 obtained from data on hair color and eye color, for which we already computed the expectations and variances of x and y, as well as the expected value of xy. So A is asking, compute the covariance of xy. Are x and y positively correlated, negatively correlated, or uncorrelated? And then part B, compute the correlation coefficient between x and y. All right, so for part A, covariance of x and y, that should just be using the covariance formula, so that shouldn't be too hard. Are x and y positively correlated? Well, positively correlated, that means that the covariance is positive. Negatively correlated means that the covariance was negative, and uncorrelated means that it was 0. So based on the result we got for the covariance, we can answer that part. Compute the correlation coefficient between x and y. Well, we can compute the correlation coefficient by, with the formula, just divide the covariance of x and y by the square root of the variance of x times the variance of y. All right, so here's the carrying out the computation of the question. Write down what we want to know, part A, part B. This is the row symbol here, which is used for correlation. So covariance of xy is equal to the expected value of xy minus the expected value of x times the expected value of y. And then we can calculate, or we can compute each of these three terms. And when we can compute it using the formula. So this actually should be the expected, or the summation of x times y times the probability of x probability of y, which is what I carried out on the right hand side. And in the end, we get covariance of xy equals expected value of xy minus expected value of x times expected value of y, and that gives us 0.1416. All right, part B, I tried to squeeze everything onto one slide, and so there's a little bit of going to be some copy paste issues, but hopefully it should be clear enough to read. All right, so we start with the definition of correlation, which is covariance of xy divided by variance of x times variance of y, all square rooted. And then we can calculate the variance of x using the formula. We can calculate the variance of y using the formula. And then now once we have variance of x, variance of y, we can now compute the correlation. And we get 0.369. All right, so question 2. Consider the two discrete random variables x and y with joint distribution derived in exercise 9.2. All right, so we have this table here. So this table is a very common table that you'll see for joint probability distributions or joint probability density functions. And you can use this for a discrete probability distribution, but for a joint probability you can't, because obviously there's infinitely many cross terms. So just a little bit of notes on reading the table. So we have our values for A here, and then we have our values for B over here. And the intersection is when A and B, so when A equals 0, B equals -1, this would be 1 over 6 is the probability. A equals 1, B equals -1, this would be 1 over 6. A equals 1, B equals +1, it's 1/2, and then A equals 2, B1 is 0. And so you can use those intersections to figure out probability of A and B. And then the summation over all of b's, so when b equals -1 and 1 for each a, gives us the probability that x equals that value of a. So for example, probability of x equals 0 is going to be probability that x equals 0 when y equals -1 plus the probability that x equals 0 when y equals +1. That's just 1/6, and then we can get 2/3 and 1/6. Similarly, over here, probability of y equals b. This is summing over the a values, right? So if we're looking at all the times that, or the probability that y equals -1, well then y could be -1 and x could be 0, 1, or 2, right? So because we don't care which value of x is, we add these probabilities together, and then we get 1/6 plus 1/6 plus 1/6 equals 1/2. So hopefully this makes sense. It should be intuitive how to read this table, but if you do not understand how to read this table, I highly recommend reviewing joint distribution functions or joint probability density functions, and definitely come and stop by office hours if you ever feel lost. All right, so expected value of xy, well, that's going to be the summation of each of the products of x and y. So we have 0 times -1, 0 times 1, 1 times -1, 1 times 1, 2 times -1, and 2 times 1. So those are each of the values that x times y can get. And the probability is the summation of the probabilities that correspond to that value. So I'll get into more of that later, but hopefully whenever you see an expectation, you should already see the formula that you need to use or realize that you need to use a formula. I know the quizzes have been open book, but I highly recommend memorizing the definition of expectation and of variance. And because we're in chapter 10, we're talking about covariance, I recommend memorizing covariance as well. All right, so note that x and y are dependent. Show that x and y are uncorrelated. All right, so to show that two variables are uncorrelated, we need to show that the covariance is equal to 0, right, by definition. Determine variance of x plus y, and then determine variance of x minus y. And if you are very familiar with the sum, with the variance of a sum, which you might, sum random variables, which you might not be given that we just did this material, but after you have seen it a while, you'll notice that you can apply some certain rules to these variances. So for example, x minus y is the same thing as x plus -1 times y, where the coefficient for y is -1. And when you expand that using the formula, the -1 actually, you square that term because it's a coefficient, and that just becomes +1. So variance of x minus y is equivalent to variance of x plus y. But we will show that later. All right, so a, expected value of xy, again, this is the formula right here, summation over all of x and y of x times y times probability of x equals x and y equals y. So when we simplify this, we get the probability of 0. Well, that's just 0 times -1 plus 0 times 1, like those probabilities, which is 1/6. And then we have -1. So the probability that it's -1 would be -1 times 1, so that's 1/6. And then -2, which is 2 times -1. And then 1, which is 1 times 1. And 2, which is 2 times 1. And the probability is 0. Carry that through, and we get that the expected value of xy is equal to 0. For B, we get probability of x. So for part B, we want to show that they are dependent, or note that they are dependent, and show that x and y are uncorrelated. Now, when they say note that x and y are dependent, they might say just assume it, but I always like to verify it for myself. So we can verify that by checking if the joint probability is equal to the product of the marginals for each entry. And if it's not for just one entry, then we already know that they are dependent. So if we look at x equals 0, y equals -1, this is equal to 0 and -1 here, which is 1/6. And this does not equal 1/12, which would be probability of x equals 0 times probability that y equals -1. So they are not independent or dependent. Or they are dependent, which is equivalent as not independent. All right, so expected value of x, we can calculate that since we know the probability that x equals each of these values. And we get 1, expected value of y is equal to 0. So the covariance is the expected value of xy minus the expected value of x times the expected value of y, and that gives us 0, so x and y are uncorrelated. Perfect. All right, so determine the variance of x plus y. So we have a formula for that, which we derived in tutorial. Variance of x plus y is equal to variance of x plus variance of y plus 2 covariance of xy, and we just showed that the covariance of xy is 0, so we will plug that in later. And then we have variance of x, which we need to compute, which is expected value of x squared minus expected value of x, variance of y, which is expected value of y squared minus expected value of y squared. And we can carry through, or we can compute these values that we need, and we get that the variance of x is 1/3 and the variance of y is equal to 1. So the variance of x plus y is 1/3 plus 1 plus 2 times 0, which is just 4/3. And then for part D, like I was mentioning earlier, we can use our formula and show that the coefficient could just be treated as -1, and because we square the coefficient here, we just get the variance of x plus variance of y plus 2 -1 covariance of xy. Okay, so that's a very important note. Initially, when I looked at this, I thought this would be exactly the same, but it actually wouldn't be the same because we have a -1 times the covariance. So it's always good to double check. It would be the same if x and y were independent, and in this case, the covariance is 0, so this term cancels out, and we do get the same value. All right, so question 3. Let u and v be two random variables from exercise 9.6. We have seen that u and v are dependent with joint probability distribution, so we have this table. Now, I'm not going to tell you how to read this table. Go back to question 2 and rewatch my explanation, but hopefully at this point you understand how to interpret this table. So determine the covariance of u and v and the correlation coefficient rho of uv. So again, this is just using the formulas, plugging in the values, and then again using the formula for covariance, and then we use the formula for the correlation coefficient. All right, so formula for the covariance, we get expected value of uv minus expected value of u, expected value of v, and we get that the first term is equal to 1/2, and then we get 1 and 1/2, so that's just equal to 0. And luckily, if you cleverly notice that if the numerator of a fraction is 0, then the whole fraction has to equal 0. So it doesn't really matter what the variance is, the covariance, the correlation coefficient will be 0. All right. So suppose x and y are discrete random variables. Question 5. Suppose x and y are discrete random variables taking values 0, 1, and 2. The following is given about the joint and marginal distributions. So again, we have this table, although this time we're missing values in the table. So probably the question is going to ask us to find the missing values, maybe compute something based on the table. All right, part 8, complete the table. All right, exactly. So in order to complete the table, we need to, well, it shows that we have a good understanding of the table if we can complete it. So we know that the sum of this column has to equal 1/3, and the sum of this column has to equal this value, the sum of this column is this value, and the sum of this row is equal to 1/3, the sum of this row is equal to 1/2. And because we know that, we can fill in the missing value here, we can fill in the missing value here, and then we can use those values to complete the table. All right, and also the sum of the values in this column at the end has to equal 1 because the probability density function for y has to, or the probability mass function, I guess that's what we're working with in this case, for y has to be, the summation over all the variables has to equal 1. All right, and we have the same thing for x. So if we add up these three values, that should equal 1 as well. So part A is complete the table. Part B, compute the expectation of x and y and the covariance between x and y. All right, so that should be pretty self-explanatory. Just use the formulas. Covariance, we also have a formula for that, so we're just going to use this formula. And part C, are x and y independent? All right, so hopefully you remember to test independence, but in order to test independent, you need to verify that every value in this table is equivalent to the product of the marginals. So every joint probability is equal to the probability of the marginals. And if that is true, then we know that they are independent, that x and y are independent. All right, so I minimized the question. It might be kind of hard to see, but there is a PDF version of the presentation that I'm giving right now, so feel free to look at that. But hopefully you can see my solution, which is the most important part. So I drew out the table here with variable names in the spots where there are missing values, and I solved them over here. Another approach would be just to fill the values directly into the table, and in fact that's probably a better approach because when you're doing part B and part C, it helps if you just need to look at the table. So anyways, we know from that part C, or that value C over here, has to be the 1/3 minus 10 over 72 minus 8 over 72. And we get that because the sum of these three values has to equal C. So we got C is 1/12. Similarly for D, we know that the sum of this row has to equal 1/2. So we can take 1/2, subtract 9 over 72 and 12 over 72 and get 5 over 24. Similarly, for E, we can look along the column and notice that the column has to sum to 1/3, and we can solve for E. And we can use a similar process to solve for G, F, I, and H. And another check that we can do at the end is if we know that we can determine the value of H based on the column, but we can also determine the value of H based on the row. And so we need to make sure that the row 1/3 H and I sums to equal 1. And if it doesn't, then we know we made a mistake. Luckily in this case it does equal 1, so we can be pretty confident that we didn't make any mistakes. There's another check we could do along the row here and summing up the values of G, 1/2, and 1/3. So we found G using 1/2 and 1/3, but we could solve for G using F and E and see if we also get 1/6. All right, so part B, we're just using the values of the table, computing the expected value of X, expected value of Y, expected value of X times Y, and then that gives us the covariance of X and Y using the expected value of XY minus expected value of X times expected value of Y. And then for part C, yes, each intersecting value is the product of the individual probabilities. In other words, probability of X equals A, Y equals B is equal to the probability of X equals A times the probability of Y equals B for all A, B. And you can do this by just plugging the probabilities into your calculator. So 1/3 times 1/3, this will give you 8 over 72, which is equivalent to 1/9, and so on and so forth. Just having this statement here is enough. You don't have to write out every single computation that you did. Yeah. All right, question 6. It's got one of those box with the cross, so I guess it's a trickier question. So suppose X and Y are discrete random variables taking values C minus 1, C, and C plus 1. The following is given about the joint and marginal distributions. So we have another one of these tables. Hopefully you remember how to interpret it. Although look here, instead of A taking on distinct values, there's C minus 1, C, and C plus 1. So it could be a little bit trickier there, but again, as long as we use the definitions that we know, the fact that C is a variable should not affect us too much. All right, so part A, take that C equals 0 and compute the expectation of X and Y and the covariance between X and Y. So we could just plug in C equals 0 here and then carry through our definitions. So part B, show that X and Y are uncorrelated no matter what the value of C is. Hint, one could compute covariance of XY, but there is a short solution using the rule on the covariance under change of units. See page 141, together with part A. And then part C, are X and Y independent? All right, and we remember how to check this. It's the same way we did in the previous. We need to make sure that the intersection between each of the probabilities is equal to the product of the marginals. All right, so for part A, I decided to keep C in because I could plug in C equals 0 at the very end just to see what the form of the expectations would look like. So we get expected value of X is equal to C, expected value of Y is equal to C, and the expected value of XY. So this got really messy, and honestly, if you plugged in 0, this would have been a lot easier to compute. But I grouped like terms and ended up getting that the covariance, or that the expected value of xy was equal to c squared. So the covariance of xy is equal to c squared minus c squared, which is 0. And that just shows that without even plugging any value of c, the covariance will always be 0, which is what part B is asking. And then part A is compute the covariance between x and y. So yeah, okay, so the covariance of x and y would be 0 if c was 0 as well. All right, and then it also says that we could use this hint. And if you were clever enough, hopefully you could think to use this hint without actually needing the hint or to use the covariance under change of units. All right, so under the chain of units rule, we have the covariance of x, y is equal to the covariance of x plus c, y plus c. And so if we set x equal to -1, 0, and 1, and y equal to -1, 0, and 1, we can see that we are actually looking at the covariance between x plus c and y plus c, right? Because to each of the random variable values, we're adding c. And because it is an additive constant, we can actually take that out. And we showed this in part 1 of the tutorial. So if you're still a little bit confused, feel free to jump back there and see how we did it. All right, so covariance of x, y, we showed that was equal to 0 in part A. And so we know that this is equivalent to the covariance of x plus c, y plus c. And so we know the covariance of x plus c, y plus c is equal to 0 for any c. All right, and so for part C, are x and y independent? The answer is no. And to show that it's not independent, we just need to show that one of the joint probabilities is not equal to the product of the marginals. So if we look at c plus 1 and c plus 1, then we get that probability is 8 over 45, and we get that from the table. But the individual probabilities would be 1/3 times 1/3, which is 1/9. And that would be 5 over 45. So the joint probability is not equal to the product of the marginals. All right, question 7. Consider the joint distribution of quick exercise 9.2 and take epsilon fixed between -4 and 1/4. All right, so we have a table here. Again, hopefully you should be pretty confident with the tables now. It shouldn't really matter what the value of each of these probabilities is. We just need to know that we use these probabilities when we're computing expected values. And covariances. So all right. So for part A, take epsilon equals 1/8 and compute covariance of x, y. Again, this is just using a formula and then plugging in epsilon equals 1/8. You can plug in epsilon equals 1/8 first. However, for me, I always like to just solve the formula and then plug in epsilon. Hopefully, it doesn't get too messy. All right, part B. Take epsilon equals 1/8 and compute the correlation coefficient or rho of x, y. And for part C, for which values of epsilon is the correlation of x and y equal to -1, 0, or 1. So we can set our correlation equal to -1 and solve for epsilon, or set our correlation equal to 0 or 1 and then solve for epsilon. And so because we have this part C where we don't plug in a specific value for epsilon, it would actually be helpful to not plug in the value of 1/8 in part A and B and to wait until part C. All right, so for part A, we have the expected value of x is equal to 1/2, and we actually didn't even need to look at these intermediate terms because we're just looking at the marginal, the expectation of just x, so we can look at this last column, and then for y, we can look at this last row. And we get the expected value of x, y. So at this point, we do need to look at the entries in the table. And we get that this is equal to 1/4 minus epsilon. So the covariance is equal to 1/4 minus epsilon minus 1/2 times 1/2, which is 1/4. So we get negative epsilon. And so the covariance of x, y, given that epsilon equals 1/8, this bar right here is given, is equal to -1/8. All right, for part B, the correlation between x and y is equal to the covariance of x, y divided by the square root of the variance of x times the variance of y. We have seen this formula a lot. Hopefully by this time you've memorized it. If not, I highly recommend memorizing it just so you know that when you see the correlation value, you can visualize what that means in terms of the covariance. All right, so variance of x is, we know the formula for that. We calculate the expected value of x squared, variance of x is equal to 1/4 then, and we know that the variance of y is equal to 1/4 as well. So the correlation between x and y is equal to negative epsilon divided by 1/4, which is equal to -4 epsilon. And this implies that the correlation between x and y is equal to -4 times 1/8, which is equal to -1/2 when epsilon is equal to 1/8. All right, and then for part C, when we're calculating the correlation of x, y, when this is equal to 1, what's the value of epsilon? And so we can solve these three individual equations, and we get that epsilon is equal to -4 when the correlation is 1, epsilon is equal to 0 when the correlation is 0, and epsilon is equal to +1/4 when the correlation is -1. All right, so for question 8, let x and y be random variables such that expected value of x equals 2, expected value of y equals 3, and variance of x equals 4. These questions should be very automatic, and in fact, if it isn't, this is a very basic understanding question. Please review the definitions of variance and expected value, or the relationship between variance and expected value, simply because these questions, we would not ask these on a quiz and test likely because they are too easy, and if you are not able to solve it right now, then you should definitely seek some extra help. All right, so show that the expected value of x squared equals 8. Well, we should be able to solve this because we have expected value of x and we have the variance of x, right? And we know that the definition of variance of x is equal to expected value of x squared minus the expected value of x squared, right? So that means we can rearrange that equation to solve for the expected value of x squared is equal to the variance of x plus the expected value of x squared, right? So that would be 4 plus 2 times 4, or sorry, 2 squared, which would be 4. So 4 plus 4 is 8. So that should be pretty easy. Determine the expectation of -2x squared plus y. And now we prove the linearity of expectations. So hopefully that rings a bell here. If it doesn't, then make sure to review that and memorize that formula or that property. And so you can carry that through. And we have expected value of x squared from a previous example. And we have expected value of y up top, so this should be straightforward. All right, and you can see it really took one line to evaluate each of these. We get 8 for part A, and B is -13. All right, so now we got question 9, the big kahuna. Another box question with the cross. So whenever you have a big word problem, I always like to, if you have a highlighter, pull out the highlighter. If you don't have a highlighter, underline key pieces of information or write it down on your piece of paper, just so you don't have to continuously read the paragraph over and over again. I like to try to read it like once or twice and then never have to look at it again. All right, so suppose the blood of 1,000 persons has to be tested to see which ones are infected by a rare disease. Suppose that the probability that the test is positive is p equals 0.001. All right, so we got a rare disease. We're testing 1,000 people, so I'd probably underline that. And we want to see which ones are infected by a rare disease. So the probability of having the disease must be pretty small. Clearly, that's not COVID, or at least the numbers are going up like crazy. So it's hard to see that. Anyways, so we have that the probability is p equals 0.001, which is relatively small. That's probably a key piece of information that we're going to need. The obvious way to proceed is to test each person, which would result in a total of 1,000 tests. That makes sense. You have 1,000 people, you test each of them once, that's 1,000. An alternative procedure is the following. Distribute the blood of the 1,000 persons over 25 groups of size 40. All right, so this part I had to read like 10 times to make sure that I fully understood it. But okay, distribute the blood of the 1,000 persons over 25 groups of size 40. 25 groups of size 40. So we have 25 groups, and in each group we have 40 persons' blood, right? 25 times 40 is equal to 1,000. Hopefully you guys can do that mentally. And so we know that, okay, this makes sense. It's a way to divide up the 1,000 people. All right. And mix half of the blood of each of the 40 persons with that of the other in each group. All right, so we have each group of persons, of 40 people. And for each of those persons, we're going to divide their blood into 2 parts, right? And we're going to take one of those parts and mix it with the same half of everybody else in that group. And so now we have one aggregated blood sample, right? So now test the aggregated blood sample of each group. When the test is negative, no one in that group has the disease because you mixed all the bloods together. If somebody had it, then the group would test positive, right? All right, when the test is positive, at least one person in the group has the disease, and in this case, one will test the other half of the blood of all 40 people in that group separately. So in this case, if the group tests positive, then at least one person in the group has the disease, and so we can test all of those second half of the 40 people. So it's going to be another 40 tests. So in total, that gives 41 tests for the group. So what we can see is if it tests positive, the group tests positive, you have to test everybody in the group. So we actually had to use 41 tests for that group of 40 people. However, when the test was negative, we only had to use one test for a group of 40 people. So let xi be the total number of tests one has to perform for the ith group using this alternative procedure. All right, so the alternative procedure is the one which we just described, right? Instead of testing everybody, we're testing each group of 40 people, and then if the group comes back positive, then we test each of the individual people. All right, so part A, describe the probability distribution of xi. In other words, list the possible values it takes on and the corresponding probabilities. So that's just the definition of the probability distribution. Yeah, so basically from here we have a calculated we have a probability that one person is tested positive. If the larger test comes back negative, then that means that all the people did not have the test. Sorry, did not test positive or tested negative, right? So we can calculate that probability, and then the complementary probability would be that at least one tested positive, and then that would require 41 tests instead of one test. All right, and part B, what is the expected number of tests for the ith group? What is the expected total number of tests? And what do you think this alternative procedure for blood testing? So what is the expected number of tests for the ith group? Sorry, just drink some water. All right. The expected number of tests for the group, well, that's just for the ith group. Well, that's just using our probability distribution function from part A. What is the expected total number of tests? All right, so this is now looking at all the groups together. And so we're looking at the expectation of a sum, and we can actually use the linearity property, which I'll get into when I actually show the solution. So that simplifies that, but you need to recognize that you can use the linearity property. And then we have, what do you think of this alternative procedure for blood testing? So I think that's more just trying to understand what the question is saying and what it's doing. Yeah. All right, so I minimize the question over here. We have 1,000 persons, p is equal to 0.01, and we have 25 groups of 40 to be tested. All right, so those are key pieces of information that I wrote down. So part A, we have xi is equal to 1 with probability nobody is infected, and that is 1 minus p to the 40. So what that means is that the probability that one person is not infected is 1 minus the probability that they are infected, right? And the probability that each person is not infected, these are individual people. There's no, you assume that they're independent. And so this gives us 0.96. And there's 40 people, so that's why we raise the power 40. All right, and then the other alternative is xi could require 41 tests for group I. So in this case, that means that there's at least one or more people that are infected. And this is equivalent to saying 1 minus the probability that nobody's infected. And so that's the probability that we're using here. In other words, it's 1 minus the probability that we just calculated. Like it says 0.039 and a bunch of decimal places. All right, for part B, we expect the value of xi, and we can use that by using the value, which is 1 times its probability, plus the other value, 41 times its probability. And that gives us 2.56919. All right, and then when we're looking at the expected value of the sum of random variables, Now it comes in handy of recognizing what the sum means. Well, this is like adding a bunch of random variables together, and we know from the linearity of expectation that the sum, or the expectation of a sum, is the sum of the expectation. All right, so we have the sum overall I of expected value of xi, and we just calculated the expected value of xi above. So now we can plug that in. It's 25 times expected value, which is 64.2298. And this is significantly fewer tests than 1,000, so that's great. That's good because we can test all the people with fewer tests. This could be good if each test is very expensive. However, in practice, there could be some other things that you might need to take into account, such as when the bloods are mixed together, maybe there could be a reaction and it could trigger a false positive, excuse me, or potentially a false negative. So those are good things to keep in mind. All right, so question 10. Consider the variables x and y from the example in section 9.2 with the joint probability density equal to f of x y is equal to 2 over 75, 2x squared y plus 2y squared. And we had x between 0 and 3, y between 1 and 2, and this gives us the marginal probability densities below. So part A, compute expected value of x, expected value of y, and expected value of x plus y. Part B, we should just use the formulas for that. Part B is compute expected value of x squared, expected value of y squared, expected value of xy, and the expected value of x plus y squared. Again, we can use formulas. For this last part, we'll have to expand the terms here and then use linearity of expectations. For part C, compute variance of x plus y, variance of x, variance of y, and check that the variance of x plus y is not equal to the variance of x plus the variance of y. All right, so you can already tell based on just looking at this question, and they've given you these lovely density functions for continuous random variables. Is going to be a lot of integration and a lot of plugging in values into your calculator / mental math. So definitely want to take it slow, take it step by step, and double check your answers in the calculator. All right, so this might be a little bit hard to read, but I want to make sure that I can fit it all onto the one page. So we have part A in this top right corner, and then we have B in the bottom left, and then part C in the bottom right. All right, so for part A, we want to calculate the expected value of x and the expected value of y. Again, we just need to use the formula for expected value of a continuous random variable. So that's x times the probability density, the marginal probability density function. Oh, I wanted to note something. So, all right, when we're looking at this question, if they didn't give us this marginal distributions for x and y, and they only gave us this joint distribution, you should be able to calculate the marginal distribution from the joint distribution. And how you do that is you integrate the joint distribution over y to get the marginal distribution of x, and you integrate the joint distribution over x to get the marginal distribution of y. So you should be able to come to these answers of these marginal distributions or the marginal densities without the joint density. All right, so the expected value of x, we can carry through our integration and we get 2.18. Expected value of y, we get 1.57. And then we get the expected value of x plus the expected value of y is equal to the expected value of x plus the expected value of y from linearity of expectations, which is 3.75. All right, and then we have expected value for part B. We have expected value of x squared, which again, we're just using the definition of expected value. We get 5.148. Expected value of y squared, which is 2.544. And then we have expected value of x times y. And this is equal to a double integration. Double integrations can sometimes be trickier, but remember that's just equivalent to integrating twice, right? So we'll integrate over one variable first, and then we'll integrate over the other. And if you do so carefully, you should end up with 3.42 or 171 over 50 as the fraction. All right, so the expected value of x plus y squared, we can expand this term in the middle, and that will give us, I should plug in. That should give us the expected value of x squared plus 2 times expected value of xy plus the expected value of y squared. And we have already computed those values and actually give us 14.532. And now for part C, we're computing the variance of x plus y, which is equal to the variance of x plus variance of y plus 2 covariance of xy. And did we compute the covariance yet? I believe, no, we have not. But we've computed all the values that we need for the covariance. Expected value of xy, expected value of x up here, and expected value of y. So we calculate the variance of x, variance of y, and the covariance of xy, which is negative 13 over 50 over 5,000. And obviously, the variance of x plus y is not equivalent to the variance of x plus the variance of y because we have this covariance term. All right, question 14. Let x and y be two random variables and let r, s, t, and u be arbitrary real numbers. So derive from the definition that the covariance of x plus y, y plus u is equal to covariance of xy. Derive from the definition that covariance of rx ty is equal to rt covariance of xy. Combine parts A and B to show covariance of Rx plus S, Ty plus U is equal to RT covariance of XY. All right, so all of these we basically did in part 1 of the tutorial, so you should know how to solve this, but I'm going to go through it one more time. Again, you just want to always start with the definition. So we want to show that the left-hand side equals right-hand side, so left-hand side is equal to covariance of x plus s, y plus u, and we can use the definition to show x plus s, y plus u, and we can use the linearity of expectations on both sides, so we can expand the left side and then use it applied on the right side, and we get that the u expected value of x, s expected value of y cancels with the other term, and then we get expected value of xy minus expected value of x times expected value of y is equal to the covariance of xy, which is the right hand side as required. All right, so for part B, we have covariance of rx ty. And we want to know, is that equal to RT covariance of XY? So we already showed this in the tutorial, but all right, we'll start with the definition on the left-hand side, and that's RxTy minus expected value of Rx times expected value of Ty. And then we can take out the R and the T because those are just constants, right? So we get RT expected value of XY minus R, we can pull that out, and then T, we can pull that out. So RT expected value of X, expected value of Y. Now we can pull an RT out of both terms, and we get expected value of xy minus expected value of x times expected value of y, which is just RT covariance xy, which is the right-hand side. Let L equals Rx, M equals Ty, and so now these L and M are random variables. We have covariance of L plus S, M plus U, which is equal to covariance of L, M from part A. And then we can substitute our L and M back in, and we get Rx, Ty, and that's equal to RT covariance xy from part B. Therefore, the covariance of Rx plus S, Ty plus U is equal to RT covariance xy. All right, question 16. Let x and y be random variables. Oh, about to sneeze, okay. All right, part A is asking express covariance of x, x plus y in terms of variance of x and covariance of y. So right away, when you see something like this, it might not be super obvious. And whenever you're trying to manipulate something that has to do with covariance or variance or any term that we can rewrite in terms of other terms, that's usually a great place to start. So covariance of x, x plus y, we can use the definition of covariance here. All right, so using the definition of covariance, we get expected value of x, x plus y, and we can use the linearity of expectations. Expected value of x squared plus expected value of xy. The second term, expected value of x, expected value of x plus y, and we can use linearity of expectations. So we get expected value of x, expected value of x, minus expected value of x, expected value of y. And then we can group like terms. So if we group this x squared with this expected value of x all squared, that's our variance of x. And then we have expected value of xy minus expected value of x, expected value of y, and that's our covariance of xy. All right, so question 19. Derive the alternative expression for the covariance, covariance xy equals expected value of xy minus expected value of x, expected value of y. And they're giving us a hint. Work out x minus expected value of x, y minus expected value of y, and use linearity of expectations. So I'm hoping that even if they didn't give you this hint, you'd be able to figure that out, because if you can't use this definition of covariance, then you must be using the original definition. Now, I always remember this definition of covariance. I mean, I just reviewed the material for chapter 10, so obviously I know the other definition, but I believe that as long as you know one of the definitions, as long as you understand what covariance is telling you, then that's the important thing. But knowing one of the definitions, if you only knew one, the second form is probably the best, and that's what we've been using throughout all these questions. So that's what I'd recommend memorizing if you had to memorize one. All right, but yeah, the original definition uses this, and so that's why they're saying to work this out first. All right, so we have left-hand side and right-hand side. So we're starting with the left-hand side. We want to show expected value of x minus expected value of x times y minus expected value of y, and we can expand these terms. That's what they told us to do, but that's what we should be doing because that's really the only step we can take at this point. And then we have expected value of xy minus expected value of y minus expected value of x times y plus expected value of x expected value of y. And we can use the linearity of expectations. Now, a key attribute property that you want to keep in mind is that the expected value of x or expected value of y is a number. It has to evaluate to a particular number. It's no longer a random variable. And I hope that makes sense. So we don't know what that number is, but we know it's a number. And it should make sense because you're looking at the average, right? The average should be a value, right? If you're averaging the probability times the outcomes of a certain random variable, that has to be a single value. And so when we're taking the expected value of a single or particular value, that's just the expected value of a constant. And so we can just bring that out of the expectation. And that's exactly what we do here. So we have expected value of xy minus expected value of x, expected value of y. So this expected value of y here, we just took it out. And we have expected value of x. So we have expected value of x, expected value of y, and then this expected value of x, expected value of y, we're just leaving that the same. And if we cancel, or if we group like terms, we can cancel. We have we have negative 2 expected value of x, expected value of y, and 1 positive. So that'll give us just negative expected value of x, expected value of y, and that's equal to the right-hand side as required. All right, last question. Question 20. Determine the correlation coefficient of u and u squared when u has a uniform 0a distribution. Here, a is a positive number. All right, so I know when you see questions like this, it might be a little bit confusing because you have a u squared, and then you have u as a uniform 0a, but what about u squared? How does that kind of fit in? And I think when you initially see this, you might rush to write something down and just regurgitate all the formulas and try to figure something out, which might work, but I think it's important to just take a breath and think about and break it down logically so that you don't end up going down the wrong path. All right? So that was a little bit abstract, but start with what we know, right? So uniform 0a, we know what that is. So potentially writing out the definition of what that distribution is and the density function associated with it could be useful. But rho of u squared, this is a formula, right? So if we're trying to determine this value, well, that's the same thing as determining the covariance of u and u squared, and divided by the variance, the square root of the variance of u and the variance of u squared, right? So now we're solving for smaller terms. So we have a formula for covariance, right? So we can break the covariance up into even smaller terms. And then we have a formula for variance and a formula for variance. So we can break up the denominator into smaller terms as well, right? So that is the correct approach you want to take instead of just writing down a bunch of equations, right? And it could take you in a random path. All right, so here's our initial equation that we're trying to figure out, right? We want to figure out, in order to figure out what the left-hand side is, we need to figure out the right-hand side, right? So covariance of u and u squared. Well, covariance of u and u squared, this is expected value of u cubed minus expected value of u, expected value of u squared. And then we know U is uniform 0A, and so we know what the density function is, right? All right, so we know we have to calculate expected value of U squared, or of U cubed, U and U squared. And you might think maybe we might need U to the power of 4 as well. And we actually do, because variance of U squared, the first term would be expected value of U to the 4th, right? And so what I did is on the right-hand side, I just computed expected value of U, expected value of U squared, expected value of U cubed, and expected value of U 4th, so that I had those values ready when I needed them when computing the values on the left-hand side over here, such as the covariance, and the variances, right? So the expectation of U, well, that's just using the formula. We have U times 1 over A du from 0 to A. And then U squared, well, that's the same thing as expected value of U, but instead of U, we're using U squared. So that's going to change the integration. U cubed, same idea. And then U fourth, U to the 4th, same principle. Right, so I get A over 2, A squared over 3, A cubed over 4, and A to the 4th over 5. One reason that it's good to compute all these values together, or like compute one, then compute the next, is so that when you're solving for the covariance of U and U squared, or variance of U or variance of U squared, you don't need to take a break and be like, oh wait, I need expected value of U squared, let's compute that, then bring it back over, then I need U cubed, then bring it back over. I already have these values ready for me to use, right? So I can plug those values in over here. I get covariance of U and U squared is equal to A cubed over 12. Variance of U is equal to expected value of U squared minus expected value of U squared. That gives us A squared over 12. And then variance of U squared is 4A to the power of 4 over 45. And now I have all the values that I need for the correlation. So the correlation coefficient, rho, of U squared is equal to A cubed over 12 divided by the square root of A squared over 12 times 4A to the power of 4th over 45. And I did some reducing here before I plugged into the calculator. Or actually, I guess I didn't need to plug it in the calculator, just left it in irrational form. I think that's what it's called. So we got the A cubes cancel out, and I get 1 over 4th divided by 1 over the square root of 15, which is just the square root of 15 divided by 4. And one important thing to note is that this answer doesn't depend on A. So A could have been any positive value greater than 0, and the correlation between U and U squared is still the square root of 15 over 4. Which is an important fact, I guess, but it won't really come in handy until you see this correlation in potentially future courses. All right, so that's everything. Lots of computation today, lots of calculations. Don't be too hard on yourself if you made some little calculation mistakes here and there. As long as you carry through your answers, you won't lose many marks on exams or quizzes. If you have any questions about any of the work that we did, or questions about some of the questions that we did not cover that you just decided to tackle, feel free to post that on Piazza. As always, my office hours are on Wednesdays from 3 to 4 p.m. And feel free to email me at steven.brock@mail.utoronto.ca if you ever want to talk about anything or ask me some questions. Please let me know if you have any feedback on the tutorial as well. Thank you very much, and best of luck with your studies.